Hello everyone, I am Rupokde. Today I am going to discuss another problem related to the function analysis which was asked in GATE 2021, and some students request me to solve this kind of problem. So today I am going to discuss this problem also. So first try to understand this kind of problem first, and after that we will try to solve it. So now look at the problem. So problem says that let C closed interval 0 and 1 be a Banach space of real valued continuous function on closed interval 0 and 1 equipped with the supremum norm, and define T such that C closed interval 0 to 1 to C closed interval 0 to 1 by T of fx equal to integration 0 to x ft dt. Let Rt denote the range space of T, and consider the following statements. And statement P say that T is bounded linear operator, and the statement Q say that T inverse such that Rt to C closed interval 0 to 1 exists and bounded. Then first option, both P and Q are true, and second option, P is true and Q is false, and third option, P is false and Q is true, and fourth option, both P and Q are false. Okay, this is our problem. Now look at this problem also related to the supremum norm on the C closed interval 0 and 1, and here says that this linear operator bounded or not, and T inverse exist or not, and T inverse bounded or not. So this problem depend on the linear operator. Okay, now we try to solve this kind of problem. So I always start with how to solve this kind of problem. So how to solve? Okay, so first recall some theorem. Recall number 1, T such that x to y, where x is a nonlinear space and y is a nonlinear space, be a linear operator, then T inverse exists if and only if T is bijective. So if T inverse exists, then T is bijective, means T is 1 1 as well as 1 2, and if T is bijective, then T inverse also exists. Okay, so this is also if and only if condition. Now recall another theorem. This is also called inverse operator theorem. Okay, so x and y are two vector space. This vector space may be real, may be complex. Okay, now we defined a linear operator T such that x to y with d of t subset of x and r of t, that is range set of t, subset of y. Clear? Then the inverse T inverse such that r of t to d of t exists if and only if t of x equal to 0 imply x equal to 0. Clear? And if T inverse exists, then T inverse is linear operator. Third part says that if dimension of d of t equal to n less than infinity and T inverse exists, then dimension of d of t equal to dimension of range of t. Clear? So this is the inverse operator theorem. So x and y are two vector space. This vector space may be real or complex, and T such that x to y be a linear operator with d of t, that is domain of the linear operator T is subset of x, and range of t is also subset of y. Then the inverse T inverse such that R of Rt to dt exists if and only T of x equal to 0 imply x equal to 0. And second says that if T inverse exists, then T inverse is a linear operator. And third says that the if dimension d of t equal to n, that means dimension d of t is finite and T inverse exists, then dimension of d of t equal to dimension of R of t. So this is the inverse operator theory. So you check T inverse exists or not by using these theorems, okay, but I use here the inverse operator theorem to solve this kind of problem. Clear? Now here operator T define C close interval 0 to 1 to C close interval 0 to 1 by T of f x equal to integration 0 to x ft dt. Clear? Now we check T is linear. Okay, now we check T is linear. So for all f and g belongs to C close interval 0 and 1, and for all alpha and beta belongs to R, and for all x belongs to close interval 0 to 1, T alpha f plus beta g x equal to integration 0 to x of alpha f plus beta g dt, and this is equal to alpha into alpha into integration 0 to x ft dt plus beta into 0 to integration 0 to x gt dt. Clear? And this is equal to alpha of t of fx plus beta t of gx. So ultimate we get t alpha f plus beta g equal to alpha tf plus beta tg for all f and g belongs to C close interval 0 and 1, and for all alpha and beta belongs to R, and for all x belongs to close interval 0 and 1. So this implies T is a linear operator. So T is a linear operator. Now we check T is bounded or not. Okay. So we find T is linear operator. Now we prove T is bounded. Okay. So T is bounded. Norm of Tfx. This is equal to maximum of x close interval 0 and 1 integration 0 to x ft dt. Clear? And this is less or equal to maximum of x belongs to close interval 0 and 1 integration 0 to x mod of x into mod of ft dt. Clear? And this is less or equal to maximum of x belongs to close interval 0 and 1 mod of x integration 0 to x, this is equal to mod of ft dt. Clear? And this is less or equal to maximum of x belongs to close interval 0 and 1, and this, since x belongs to close interval 0 and 1, so modulus of x equal to x, and this is norm of f integration 0 to x dt. Clear? And this is equal to maximum of x belongs to close interval 0 and 1 into x square into norm of f, and maximum of x square equal to 1 in closing. So maximum of x square for x belongs to closed interval 0 and 1 equal to 1. So ultimate we get this is equal to norm of f. So finally we get norm of Tf x less or equal to norm of f. Okay, so this implies norm of Tf less or equal to norm of f. So this implies norm of Tf by norm of f less or equal to 1. So that means norm of t less or equal to 1. This implies t is bounded. So this implies t is bounded. So ultimate we get norm of t less or equal to 1. Norm of t less or equal to 1. This is number 1. Clear? Now we claim that norm of t equal to 1. Okay. So we prove that norm of t greater or equal to 1. So take f of t equal to 1 for all t belongs to closed interval 0 and 1. Then norm of f equal to 1 for all t belongs to closed interval 0 and 1. Clear? Now t of fx, this is equal to integration 0 to x ft dt, and this is equal to integration 0 to x into 1 dt, and this is equal to x square. So norm of tfx, this is equal to maximum of x closed interval 0 and 1 x square, and this is equal to 1. Now 1 equal to norm of tf, this is less or equal to norm of t into norm of f, and norm of f equal to 1. So this is equal to, this imply 1 less or equal to norm of t. So ultimate we get norm of t greater or equal to 1. So this is number 2. So combining 1 and 2 we get norm of t equal to 1. Clear? So finally we get norm of t equal to 1. So t is a bounded linear operator with norm of t equal to 1. Now we check T inverse exists or not. Okay, now we check T inverse exists or not by inverse operator theory. Okay, now for all f belongs to C closed interval 0 and 1, T fx equal to 0 for all x belongs to closed interval 0 and 1. Clear? So that means integration 0 to x ft dt, this is equal to 0 for all x belongs to closed interval 0 and 1. Clear? So this implies x into integration 0 to x ft dt, this is equal to 0 for all x belongs to closed interval 0 and 1, and this implies integration 0 to x ft dt, this is equal to 0 for all x belongs to open 0 close 1. Now differentiating with respect to x, we get f of x equal to 0 for all x belongs to open 0 close 1. Okay, since f(x) is continuous function in C closed interval 0 and 1, so f of 0 equal to 0. So ultimate we get f of x equal to 0 for all x belongs to closed interval 0 and 1. So t of fx equal to 0 imply f of x equal to 0. That means T inverse exists. That means T inverse exists. So T inverse exists. Okay. Now we check T inverse bounded or not. Okay. For T inverse bounded or not. Let fn t equal to t to the power n for all t belongs to closed interval 0 and 1. Okay. Then norm of fn t equal to maximum of t belongs to closed interval 0 and 1 t to the power n. This is equal to 1. Okay. Now gnx equal to tfnx. This is equal to integration 0 to x into t to the power n dt, and this is equal to integration 0 to x, this is equal to x into 0 to x t to the power n dt, and this is equal to x into t to the power n plus 1 divided by n plus 1 integration 0 to x. We get x to the power n plus 1, x to the power n plus 2 by n plus 1. Okay. So the value of this integration equal to this. Now norm of g and x equal to supremum of or maximum of x belongs to closed interval 0 and 1 x to the power n plus 2 divided by n plus 1, and this is equal to 1 by n plus 1. Clear? So norm of g and x, this is equal to t of f and x equal to 1 by n plus 1. Now norm of t, this is equal to, now norm of t, this is equal to maximum of x belongs to closed interval 0 and 1 norm of tf, norm of tfn by norm of fn, and this is equal to 1 by n plus equal to 1 by n plus 1 by 1. So ultimate we get 1 by n plus 1, and this is less than 1 for all n belongs to n. So this imply norm of, this imply t is bounded. So this imply t is bounded. Now fn t equal to t to the power n for all t belongs to closed interval 0 and 1. Clear? And norm of gn x, this is equal to norm of t fn x, this is equal to 1 by n plus 1. Okay, and norm of fn t, this is equal to 1. So ultimate we get 3 results. Okay, so gnx equal to t of fn x for all n belongs to capital N and x belongs to closed interval 0 and 1. Since T inverse exists, so T inverse gnx, this is equal to fnx. Now norm of T inverse gnx, this is equal to norm of fn x, and you know that norm of fn x equal to 1. So this is equal to 1. Now if T inverse is bounded linear operator, then 1 equal to T inverse gnx, this is less or equal to norm of T inverse into norm of gnx. Clear? And norm of gnx equal to 1 by n plus 1. This implies 1 less or equal to norm of T inverse into 1 by n plus 1. This implies norm of T inverse greater or equal to n plus 1. N belongs to capital N. So this implies this implies T inverse is not bounded. So ultimate we get T inverse exists, but T inverse is not bounded. Now look at the options. So the statement P says that T is bounded linear operator. From this result, T is bounded linear operator with norm of T equal to 1. So according to this result, P is true. And Q, the statement Q say that T inverse such that RT to C closed interval 0 and 1 exist and bounded. And here says that T inverse exists, but T inverse is not bounded. So the statement Q is also false. So the statement P is true and the statement Q is false. So the second option is also correct. So B is also correct. So our answer is B. So this is the way to approach this kind of problem. So this problem is related to the basic concept on the linear operator bounded or not. Okay, so always focus on the basic concept. If your basic is clear, then you will be able to solve this kind of problem and learn mathematics and work hard, and subscribe my channel for more update. And again, thank you and take care.